Hello and welcome to my talk called Scooby RAM, Where Are You? If you remember some cartoons from when you were a child, you're probably correct. If you are thinking of any copyrighted works, this is absolutely nothing to do with those. If you have phones, you can do this. The questions in there are easy and there are no prizes, and you do not have to leave your data. Good, I'll assume it worked. So I have to quote a friend. He says that truly great people quote themselves. I'm only quoting them because I think this is an awesome quote. My name is Andrzej Grzesik, or I go by Axe. I'm a co-founder of Datalinks, the 7 like a wolf-like looking t-shirt that has a stand over there. I know many of you enjoyed it. Happy to hear that. I have a Twitter, I have an email. If you want to talk about Datalinks, let's do it at the booth. Some things about me, I keep using the wrong Geekon logo. I'm also a Java champion, Java 1 rockstar from when it was still a thing. And I'm affiliated with some groups that have those logos. Some of them might not exist anymore. I think Krakow Hadoop user group has migrated. I also love to write jokes, which are mostly a reminder for me to drink. And if you have any questions, I know that there is a microphone somewhere in the room, so just wave and signal. Or alternatively, if you scream loud enough so that I hear it, I can try to repeat it so that the YouTube audience is happy. And then we can go through that. That's the last chance. I assume everybody has gone through it. And I can see the answers to the quiz. I don't see anybody on JDK 8, which is amazing. Sadly, this is not what somebody in the audience told me in person yesterday, so yeah. To memory. So we're going to talk about memory. There was an awesome talk about how CPUs work in the morning, so I don't have to explain that already. The first question would be, or the first thing that we should think about is, where do bytes live? Has anybody ever seen a byte in memory? Well, somebody could say, if you take a magnifying glass and you look into that structure very, very closely, you'll find a byte. And I could say to that, yeah, so how do you read exactly one? And then, devil is in the details. You don't read one byte. You usually read a line, so you read them in groups. For example, this model of EPIC has a cache line of this many bytes, which means you read a whole cache line because you cannot get less, and if you want just 1 byte, you put a mask on top of that, which means reading just 1 byte from memory is kinda hard. Kinda being a nice way of saying impossible, or reading a single byte is an illusion, you never do that. That is important, and we will see why. But let's continue with the journey. I now have some specs from old CPUs. There is a reason why they are old, but 2013, Xeon had 10 cores, could do 20 threads because it could do hyper-threading, and it had a bandwidth of this much, 6 gigabytes per core. Then we're looking at the next generation of something similar, 4.8 gigabytes per core. Is it a lot? Is it not a lot? I'll leave that to you. Current CPUs can get 128 cores. That is a lot of cores. There is a problem with memory bandwidth. It's not really growing as quickly. If we look at consumer-grade CPUs, we'll see that still 6 point something gigabytes per core. That is not crazy. That is not growing. And that is a thing. Moore's law is very happy. CPUs grow however they want. The problem is memory performance is kind of behind, or it grows slower, which means the gap goes bigger and bigger and bigger. There are technical workarounds that try to not to allow this chasm to grow too wide, but still processors get faster at computing, faster than memory gets faster. One of the effects of that is we get next and, well, further and further generations of DDR. For example, current one is called DDR5, which has more bandwidth usual than DDR4. It also has lower power consumption, which is really important if you have something like 2 terabytes of RAM in a computer, or 4 terabytes, like think big servers, because reading that much memory at 60 gigabytes per second would take a while. That's effectively how much it would take to read the entire memory just from start to beginning. So we get other effects on servers, more channels. Probably everybody here has heard about dual channel memory. There are more channels available. You can get 4 channels, you can get 12 channels. There are some benefits to do that. Sadly, this is not just multiplying. There is more complexity to how memory works. Maybe that's worth of a talk from somebody someday. The point is memory is getting faster. Accessing memory in general is getting faster, but this is not rapidly, massively faster. And the unexpected effect, which explains why I use the old CPUs to show the data, is Intel stopped publishing memory bandwidth. They don't. For new CPUs we checked today, it wasn't there. The important bit to remember, memory is rather fast, caches are faster. If you can be predictable with your code, that is not a problematic thing, but it's not infinitely fast. And with that, a reminder for me to drink. So if we talk about Java and memory, one thing comes into play, and that's going to be garbage collection. So probably everybody knows what garbage collection is. Some people like it, some people don't like it. Garbage collection is effectively what allows us to not have to write delete by hand and not have to wait for the compilation forever until borrow checker does its job, which means it's rather nice because it is almost like magic. It's now very good. It is rather fast. I think everybody here is familiar with GC enough, so that's enough. Sadly, this does not mean that Java cannot run out of memory or cannot have any memory problems. That would be too good. I would expect most of you have seen this one, the classic out of memory already. Java out of memory error, Java heap space. Has anybody not seen that ever while coding? Or everybody's sleepy because it's after lunch. It's post-lunch, so yeah, hands are heavy, I know. If you have, you could start wondering why does it happen? And not because you have allocated too much, but why does it happen as in what are the settings being used? There is a thing called JVM ergonomics. So GC and memory settings that the JVM will apply depending on available hardware, because it has to set those GC thread counts to something. It has to set the sizes to something, and it cannot be always 12 megabytes, because if you run it on a server box, that would be kind of stupid. So instead, it uses some different logic. I asked about Java versions because in JDK8, it used to do that. If you had 2 or more physical processors or 2 or more gigabytes of physical memory, your computer was considered a server. So here I have a server in my hand, according to Java. That continues to be the thing. Server means it will go with G1. Precisely in the source code, it says that if the memory amount is more than 1792 megabytes, you don't have to remember that, and there will not be a quiz asking for the specific value later. So no need to focus on it. The second metric used is cores. But what really is a core? On-prem physical hardware, that answer is usually easy. In the cloud, on a layer of layers of virtualized VMs in Kubernetes through a containerized C-grouped something, it varies. One thing to remember is there is something called milli-cores, so CPU usage quota. Thousands of milli units translates to 1 core. That's effectively how it works. There is a caveat, of course, because cloud providers, when they say cores, it's complicated. For example, we found that with Michał just before, just to have an example, 2 virtual CPUs inside some machines in GCP are supported by 1 physical core on the underlying hardware. Which means if you get a machine with 8 vCPUs, you might effectively be given 4 real cores under the hood. It might be different for some kinds of machines, and it might be different on your cloud platform, so do check. But it's something to be mindful of. It's not one-to-one, or it's not that easy. Also, quotas. 1,000 millicores, it's a core. Cool. But it's the total amount of CPU time a container is being given in a unit of time. nobody says that is going to be given in one unit. It might be across multiple cores 10 times for a tenth of a second. The math still adds up. And Java, of course, has many more threads than just your application. There is GC threads, there are compiler threads, there might be something else running there. If you're running in a container that is also running something else, hey, that's there. Kubernetes usually cannot tell your application and GC threads apart, which means if your GC is running very heavily, your application doesn't get to run. And hey, well, Kubernetes did its job. So since JDK 11 plus, there are more options. The defaults are going to be G1, which is actually not bad. Number of GC threads is going to be limited by what's available on the hardware. The initials and the max is set as on the slide. You don't have to remember that. If anybody wants the slide, drop me an email. I'll be happy to share. But if somebody's running in a Docker or another container, then since that update, container support has been merged in, which means you can also refer to RAM as percentage. So if you keep getting bigger and bigger containers, you don't have to specify the size in percentages. I actually don't recommend it, so I don't like the percentages. Usually you run on a couple of classes of machines, just set the values depending on the machine size so that you know exactly what you're running with. That's just much easier for troubleshooting because you don't have to do the math every single time you worry about why did it run out of memory or what actually was too big. Setting processor count is useful because that is how different pools are initialized, so you can override it. Also, there are some funny bugs with some hypervisors misrepresenting something or effectively lying to your application. Maybe because they want to support funny application licensing schemes, maybe something else. Useful to know. Another useful thing to know is Java -x show system settings. You can do that. It will tell you what it sees. So if you're investigating, it's quite nice. One observation here, JVMs run much better if they have more than one CPU available. So if you're doing something like a fleet of 10 0.4 core VMs, I would recommend to do less containers, but bigger. Ideally, 2 cores is decent. Another thing is Java likes a reasonable amount of RAM. What is reasonable? It depends on the use case. It is possible to have a JVM that runs happily with 64 gigs of RAM. It is also possible to have a JVM that runs happily with 64 megabytes. If you have a workload that is very well self-contained, good, but you have to know. Also, if you are running with tiny amounts of memory, Graal can help or can work nicely, but I'm saying can, I'm not saying will. That means that you have to test your application and your specific use case because it varies. There are no promises here. So JVM in a container, active processor count, you set that to n. We've discussed max RAM percentage versus specific value. Specific value wins. Does the active processor count work? Well, yeah. I can override it to whatever I want, and it even runs in Docker. It's not going to be a live demo because I would just show the same, and life is short. We don't have the time. So I know some people do that. That does not mean that Christmas equals something. That usually means that people want the heap to be sized to something specific and not fluctuate, which is, for some cases, actually a very good thing to do. But that is also not enough. Why? Because A, Java is smart, and B, operating systems, mostly Linux, because I do not know how Windows works, and I have no idea if anything of this applies to Windows, are lazy. So they will give memory to the process when it actually needs them. So you can ask Java to pre-touch all the pages, so that all of the pages are actually given to the Java process, so that you have a contiguous chunk of memory. But you also have to disable adaptive size policy. Without that, XMX equals XMS might not work. That part we talked about. Operating systems are great, and they are lazy, and we'll talk about a few other examples in which they are lazy more. And adaptive size policy, you want to disable it, so that when heap occupancy is crossing levels, JVM is not going to try to acquire or release memory. Yes, it should not, but hey, year is 2025, we are happy, and you know that any problem becomes a different problem in Java. For example, this one. But I'm not going to bash this awesome language that has no community dramas. Instead, I'm going to bring Kubernetes and in a specific cloud of your choosing into the mix. So first of all, I keep running all the things I run with glibc. I know some people are passionate about Alpine. I can only say I know I am avoiding lots of problems by sticking to glibc. And if there are problems, glibc is usually a safer default for debugging. That does not mean you have to switch, but that's just what I do, and that's what works for me. Kubernetes has something that also kills things out of memory. If your container exceeds what it has been allowed, it's going to be killed. Have you ever had a container die on you? Probably. Are you sleepy after lunch, after the awesome discussion panel? Probably as well. So, in the second part, or in the current part, we're going to talk about those rectangles. One of them we're not going to talk about too much, which are symbols, because actually that doesn't give too many problems, and usually people don't care about it that much. So let's start with heap and the GC overhead. So the Java process memory usually has memory that belongs to those. There is heap, there is metaspace, what used to be permgen, where classes are. There is off heap, which means anything that relates to the process but is not on those two. There is code cache, so that's where your JIT code compilation results sit. There are symbols and there are thread stacks. So if you have threads, they need the stacks somewhere. Heap and GC overhead. What do you do if you have a problem? Obviously, you take a heap dump. How do you take a heap dump? Who knows a way? I assume everybody. One popular thing is this one. And it used to work absolutely amazing in the time of bare metal and normal hardware. In containers, it can also work if you have the space and some other bits. There is one new option that people might not know about, which is you can ask the JVM when it does a heap dump to gzip it. So you pay time for space, see whether it works for you and whether it's worth the effort. So how do you take a heap dump? The current way is to use something called JCMD. There are other ways, but we'll look at this one and imagine this is a live demo. So we list the processes, we see what options are supported by that process, and we ask it to do a heap dump, and It has generated this much bytes in this many seconds. And this is one of the few examples that I'm doing on a Mac. Usually performance things and Macs don't mix that well, as in I usually target Linuxes and I do things on Linux, not on OS X. But as a typewriter and a presentation machine, it works great. Kubernetes and heap dumps. Where are the problems? Anybody knows already? Yeah. If you want a Mac for activity, obviously you can claim one. One thing is you need to deliver this heap dump somewhere. So you either need to mount a volume or ship it to S3 or something like S3, or just deliver it somewhere, have something writable. Some people like to do containers without anything writable to them. And then if you want to write a heap dump, that's not going to work. So there is that. There is another caveat. Health check, heartbeat, whatever you want to call it. If there is a container that is expected to every second respond to a tick, and you tick it, and it's busy making a heap dump, and it doesn't again, and then it gets killed, and you don't have a heap dump, and you don't have the troublesome container. Take it out of the monitoring pool, maybe add another machine, and then when it's safe to do so, do the heap dump. Your GPT of choice will help you with that. Your ops team of choice that you love and respect and give repeatable drinks to will also help you with that. There are tutorials on that. So you have to also ship it somehow of the Kubernetes cluster, but that's again your deployment story. And there comes another caveat. A heap dump contains everything in the heap. If you keep customer email addresses in the heap, they will be there. If you have private data in the heap, they will be there. There is a very useful tool released by the PayPal people that I know that Mateusz knows about as well, which effectively does this. So rather than having raw strings, it will blank them and make it sanitized, so it becomes safe to ship to developers, maybe safe to put on something accessible for people outside of the organization if you have that. I know some people use it, I know some people love it. I have not yet met a person that has looked at it and said that this doesn't do enough. But if your InfoSec raises questions, it might help you. Okay, let's say we have a heap dump, we're happy. How do you speak to one? Well, obviously with anger and authority, and it's 2 a.m., so you have to be a bit quiet as well. But most of the tools that you know and love can let you open a heap dump and analyze it. One thing that I would recommend is, first of all, dropping me an email after the presentation, so I'm happy to share the slides, really. JProfiler and YORKit, very good. NetBeans Profiler is very good. Visual VM is that component inside it. Eclipse Memory Analyzer is probably where you can start. It's what a lot of people use, and it's free, and it's open source, and great. It's also Eclipse, which means it has native controls. JDK Mission Control can help you as well, and there are other tools, certainly, that I'm not aware of, or I was too lazy to list. If you want to open a heap dump, what will happen? Well, there are quirks first. A heap dump from a 60 gig heap can be bigger than 16 gigs. Why? Because not only you have instances, but you have thread stacks, you have constants, you have other things which were loaded. That information has to be somewhere. Your tools might freeze. They themselves might run out of memory. And if you're trying to open a server-grade 90 gigs of heap, you will need a lot of RAM to do that, and it will take a while. A while, like, depending on the tool, couple minutes, sometimes half an hour. Can it be longer? Yes. Why I also mentioned many tools on the slide before is some tools sometimes fail when opening some heaps, and then those same tools are happy with others. That just happens. I accept it as a fact of life, and you should know about it so that you don't get discouraged if you actually need to do that. It happens. Loading a large heap dump, so maybe loading a server-grade big box heap dump might require a server-grade machine to analyze, and that's fine. That's normal. So what can we get there? That's a screenshot from Eclipse Memory Analyzer. There is a bunch of, there is a summary, there is a bunch of reports. You can take a couple of actions. You can list a number of instances. You can see what are the biggest objects. You can see what are the expensive object trees. You can see what are the duplicates, for example, duplicate strings or duplicate objects. You can ask it to tell you what are the leak suspects. Other tools have exactly the same or extremely similar reports, so it really doesn't matter which one you start with. Duplicate strings we have here, again, duplicate objects, zero-length arrays. Are they a problem? It depends. But we have some very smart people in the room, so I brought in a quiz. The quiz, of course, can generate a mug if you want it. There is a heap dump that had 24 million of Java-lang strings. That is a bit excessive. That number kept growing. I can even be nice to you, and I can show you the code that allocates them. Can you see the problem? Oh, I know you can see the problem because the problem is right there. Or specifically, anybody knows the solution? If you're invoking Java from C or C++, you have to deallocate the local reference, because otherwise you've lost the reference, but you've made it, and then you keep those strings cannot be garbage collected. It's a very painful thing to debug, but if you have Java method invocation calling JVM methods from outside and giving it strings, remember about that. That is not fun to debug, but it happens. Let's move on. Recent Javas, so 24 and 25, brought something called compact object headers. Every object in Java has a header. It used to be big. It can be made smaller. Smaller means less memory pressure and less space being used by that. Give it a try. It might be amazing. It also means, because we know that the memory bandwidth is limited, that your applications might become running faster if you're on a modern JDK. But we also know that Java is not only heap. Because we talked about the heap, and there is some bookmarking overhead, depending on which garbage collector algorithm you use. The overhead will vary, because garbage collector has to remember what it visited. It has to have all the bookkeeping that it requires. So, metaspace. Metaspace defaults to sometimes unlimited, sometimes something else. If you want to know that, or if you know that your application never uses more than X metaspace because it has a constant load of classes and I don't know, 30 megabytes is enough, good. If it fluctuates, maybe give it a bit more, but if you limit it to something, you know that it cannot exceed, or you will get a notification. It's usually a good practice to set it to something in production so that you don't get surprises, because those surprises are the signal that you want. Because in a container, everything is limited, because you have limits and we're trying to work within them. Then you have the off-heap. Debugging off-heap is a lot of joy for a couple of reasons. First of all, max direct memory size, so the memory limit for byte buffers defaults to XMX, which means you think that you have a container that has 16 gigs, we'll give it XMX of 12 gig, and you've also set the byte buffer memory consumption limit to 12 gigs, which means if they ever grow that big, they will never grow that big because the container is going to out of memory before that. You can monitor your byte buffer usage here in that MX bean, for example, but do set it to something specific. You will have to run experiments. It will probably, maybe, depending on what your code base does, end up 60%, 70% of memory of the container goes to the heap, maybe 20% goes to the buffers. Maybe something else. It really varies depending on the application, but do set it to something. Apart from byte buffers, there is also native memory, because Java can call C, and there are some C in Java as well. And there is a caveat. Java has a feature called native memory tracking. Sounds great. We load a DLL, we call the methods from there, that's going to give us information about it. Not so much, because this only tracks JVM mallocs. So if you do JNI, it will not tell you about it, even though it would be really, 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 really nice if it would. It has a small performance penalty as well for being able to track it. But if you're having a fire going around and you cannot just bump the memory limits, then it's useful to know. If you need to know the memory consumption of those JNI mallocs and everything else, what you can do, for example, is replace the malloc with gmalloc. That's how you do it. This thing works. I've used it. I know other people also have used it. It works great if you need it. You can also use async profiler. IntelliJ has it. You can do it through the command line. And since we're talking about native memory also has something called trim native heap interval. This is how often the JVM should try to trim the native heap. Caveat, only on Linux. Caveat, only with glibc. I've mentioned glibc before. This is just another supporting reason. The default, sadly, is 0. So maybe what, in case of problems, you will need is just to enable this feature so that JVM will try to trim this. You can also use JCMD to do it, to tell it to do it right now. So we've talked about that. Thread stacks. What are thread stacks? Well, every thread, every real thread, as opposed to virtual thread, will have their frames somewhere. I know some people will like to say, hey, every thread is roughly 1.5 to 2 megabytes of memory, and it can grow up to there. There is more complexity around how big it is and how it's configured in your operating system. But the really good thing about Linux, the operating system, is that it's lazy. So if you have very short stack traces, so your stacks are this size, not that size, then threads will take less memory because they don't need to, because they don't need those stack frames. And that means that threads will take less memory. Still, if you are launching thousands of threads, they will take a lot of memory. And if you control it or control your pools, it might be why your container or something runs out of. What else is there? There are symbols. Symbols we're not going to talk about too much because they don't generate too many problems. And there is code cache. Code cache, so where JIT puts its optimized code. If you have a big code base, lots of jars, large application, it runs for a month, you might run out of code cache. So JIT will not have enough space where to put its things. The default is 48 megs. It might not be enough. You can also ask Java, the virtual machine, to print code cache, which means it will start logging how much it's using. So if you are observing slowdowns in your application or you are just curious, you can see, hey, what's happening? And that will tell you whether maybe you need to increase the limit, or maybe you're actually always under 20 megabytes and you can save 20. So we've talked about that. We'll soon go into talking about throughput. Because we already know that garbage collector is great. It runs while our application also works, which means we don't have to run delete. And that means that you will have something called GC induces pause times in your application. Usually, those are terrible if you're in a latency-sensitive domain. Or maybe they are not a problem because you're optimizing for the total wall clock duration of a process and you have a couple of hours and you want to shave 5 minutes and you don't care if it pauses in the middle. The requirements vary. But we know that with a large heap, our CPU can only process so much gigabytes per second. So one way around it, or differently, there is a very nasty problem that can show up in your JVM. Has anybody not seen GC overhead limit exceeded? I expect some people haven't, because you need to wait a bit for that to happen. Also, when you've seen your Java process run, it's full on memory, it's spinning cores, it doesn't seem to make any progress, it might be that. And it's a particularly nasty thing because the limit in which this exception is going to happen is set to, by default, 98%. So if GC exceeds 98% of time, so application gets to run less than 2% of time, only then you will see it. So you could say, hey, but you never said which time unit is being evaluated this under. And you would be extremely correct. It's not specified, unless you check the source code. So this means it only will manifest itself after a long wait. And if there is a tiny progress, maybe your application runs for 2.5% of time, then that's not giving any problems. And if we look at 2.5% of 100 minutes, and GC is spending 97.5, and the rest is your application, I think you already have a problem. So you might want to lower it to something much more radical and see if you have problems. Or if you suspect your application is doing that, well, that might be a culprit. So how would you know? Excellent question. First of all, enable GC logging. That's known. In old Java, you used to do that. In newer Java, you do that. If you want to know more of the options, you read that. Don't take pictures of those slides. This is just so that you know that there is there. If you need to migrate an old application, there is also a tutorial. Great. So let's say you log those GC logs somewhere. Maybe even not into DevNull, but actually onto a disk. But if it's a slow device, at least in modern Java, GC logging is async. It used to be not. So you could induce GC pauses because of GC logging being written. Some people are still on old JVMs, sadly. What can a GC log tell us? You probably know that is an example GC log. Don't try to read it. Don't try to memorize it. Don't try to write regular expressions to parse it. That would be very bad. A pain. So the joke is, what is the plural of regex? Regrets. I completely agree, especially if somebody tries to do that, because the format of that also changes from every version of Java. There are tools. There are excellent tools. There is a ton of tools available. You can pick one that you like. You can pick one that's not on the list and also you like. It's up to you. Don't do it manually. What you will want to do though is this. Print flags final. So list all of the options that Java has set and their values. Why? Oh, it's very easy because some flags might trigger changes in the others. And you think that you've set this and that and Java has overridden because of your previous change. Or maybe there is an overzealous PM somewhere along the deployment pipeline that has his magic script which injects some flags and then actually this is what makes your application unhappy. Starting with a sane set of flags so that you know what you're debugging helps. One thing to note, they can change between releases. And what is the point of reference that I would recommend? Excellent question. One is, the ultimate is JDK sources. And the second one is a website called Chris Who Codes that has a reference. For all the, or most of the Java versions and releases out there, it has all the flags, it has descriptions, and you can, for example, see that there is an out-of-memory error, run path of script, it has a search, it's great. So, still, we've done this, our application doesn't crash, but it's slow. What could be the reason? One reason is that. Lots of strings. There is a very nice, what looks like a serval bullet, but comes with caveats, option available. It's called string deduplication. This is an option in which the garbage collector will evaluate the underlying arrays, and if it decides that they are the same, it will deduplicate. Strings are immutable, so this is very great and in theory very useful. But if you have lots of strings, and GC will have to do that a lot, and they actually are not duplicates, this means wasted effort. But if you do not have the luxury of changing or fixing the code and you want a quick win, it might be something that helps. I know that people have seen good wins, quick wins with that option, and I also know that people have seen situations in which this has been completely demoralizing. So I cannot advertise as do run it. No, check if it helps in your particular use case for every specific application, because it will vary. Yeah. It can also be that your heap is full of capital primitives. Sadly, we don't have the JEPs that we are all waiting for yet in the JVM. And that means that anytime you want to put a primitive type in a collection, you cannot use the primitive type, so you cannot use int, you cannot use lowercase long, you have to put a big long. Where's the problem? Well, first of all, you have a lot of objects. Second, you will probably have quite some duplicates. Three, that means extra memory pressure, and we don't like memory pressure. So if we have a sample application, which it doesn't matter what it did, over 2 minutes, that was the allocation profile of that application, and the culprit being investigated was an array list of capital longs. After changing that to a long array list, so a specialized collection type, which does exactly the same, has the same API, it just under the hood stores lowercase long, so the primitives, the memory pressure has dropped significantly. Hey, but that's just a few hundred megabytes over 2 minutes. Does it really matter? It can. Runtime comparison of two cases. At first, for small inputs, for small sizes, it didn't really matter. But for large, the duration of one was 769 seconds. The other one was 513. That means 4 minutes faster just because of a single collection replacement. That sounds insane, and this is just because of those wrappers and having to move that memory back and forth all the time. So if your software does a lot of numerics and you have hash maps, whatever of numbers, specialized collection types are extremely good. Do give them a try. If you need an example, this is just one of the options. There is many. I will not tell you which one is the best because I do not consider that there is the best. They are all very good, and using any is better than using none. So how are we on time? We're good. So another useful thing is something called no GCGC. If you're debugging, evaluating, testing things out, how long is my application able to run without crashing because it runs out of memory? It's a very good proxy for how much does it allocate. There is a thing for that something called epsilon. It's a no-op garbage collector. It's a garbage collector that doesn't do anything. And you use it like this. If you've participated in the 1 billion row challenge, you will see that a lot of people actually have tried it and have used it. But before you say, hey, let's give our application a massive chunk of memory and use no GCGC and it will be faster, not so quick, because no GCGC really does nothing, which means if your memory is fragmented, it will remain fragmented. A normal GC is moving things around all the time, which is very beneficial because it's not garbage useful, garbage useful. If you have seen the morning talk about CPUs, about cache misses, a garbage collector that actually moves things closer and more predictably is a helpful thing. But it might be useful. One thing that talks about is allocation profiling. Another way to do allocation profiling is, for example, with a Visual VM or NetBeans Profiler. So what do? Well, this is Visual VM. You click on a process, you click on a button, the one that says Profiler. You say memory, you say which classes you would like to profile, and now you wait. And you let the application run for a bit, and then you see what generates garbage and allocations and how much. This will be much slower than normal, so don't run this in production or don't run this on all the applications, just one specific host that only supports a fraction of your users. And you might learn something. The tricky bit is you might, because there is no guarantee that the problem is really there, because as you've seen, we've covered a bunch of things. And the answer to why is my application slow or dying is usually it depends or it's complicated. Let's talk about it. This is my daily rate. So with that, I can get to the thank you. If you want the slides, take a picture of my email, drop me an email with feedback, and I'm very happy to share them with you. And we have plenty of time for questions. Somebody was being a bit inconsistent with how much time I had, so I thought 45 minutes, but we actually have 15, so it's great. One question that I know is going to materialize is, when would I tune? First of all, when you have something that requires tuning, sometimes it's just easier to give half a gig, 2 gigs extra memory to your process and not have a problem because it's a single instance or it's a couple of instances and nobody cares. And that sometimes happens. Sometimes you actually care about what happens, or you're running a heavily used system and you want it to be faster because you have an SLA that you need to adhere to, and then you will need to tune. In order to tune, you need to know how to tune, or you need to read books and play with things, or very important, when you cannot change the code. So a team or an existing application has been given to you, and you need to make it work faster, but you cannot peek under the hood because maybe there is an obfuscated jar and you don't have the source code and you cannot recompile and nobody knows why it's like that, but it's like that. How to tune? There is this awesome book that Amazon claims has been released in the year 1900. I don't fully believe them, but the book is still good, even though it's a bit old according to Amazon. Look at those areas. We've talked about them, and I think I can leave with that slide. Any questions in the room that I need to answer? No, excellent. So this is where you do that and that repeatedly. Thank you.